we've seen an example to where we've used the secant trig substitution. We've seen a couple examples where we use a sine substitution. In this example, we're going to take a look at being able to use our tangent substitution. So we have this integral x cubed x squared plus 4. It'd be nice if these two were reversed. If it was x squared times x cubed plus 4, because then we could just use a u substitution, which is a lot easier than a trig substitution, but we're relegated to the trig sub. Clearly, a squared is going to be 4 for this, and that means a is going to be equal to 2. And so our trig substitution, because there's a plus sign, and anytime there's a plus, you don't have to worry about whether it's going to be secant or secant or sine. It's always going to be just the tangent function. So we're going to let x be equal to the two tangents of theta. We're going to get our triangle, divide by 2, tan theta. And we know that the opposite over hypotenuse is the tangent function for our right triangle definition. So we have x, we have 2, and we know that since a squared plus b squared equals c squared, c is going to be equal to the square root of a squared plus b squared, or x squared plus 4, or 4 plus x squared. Doesn't matter because it's commutative either way. All right, we're also going to solve for dx. So the derivative of 2 tangent theta is going to be 2 secant square theta d theta. And it may or may not be relevant for this problem, but we can also solve for theta. As we saw in the last problem, it was useful for us to be able to solve for theta by itself. So we could just take the arctan of both sides and get the theta if we chose to. All right. It may or may not, again, be useful for this problem. All right. Now we're going to substitute. So we now have the integral. Instead of x, we're going to substitute 2 tangents of theta. Instead of dx, we're going to substitute 2 secant squares of theta. So we're going to get 2 tan theta cubed square root 2 tan theta square plus 4 times our dx 2 sec square theta d theta. All right, now let's simplify the radical expression. All right, so this is going to be the square root of 4 tan square theta plus 4. We can factor out the 4, and we'll be left with tan square plus 1, tan square theta plus 1. And we know that that's going to be secant square by our Pythagorean identity. It's going to be 4 sec square theta, or 2 sec theta for our substitution, or at least for the simplification of this radical. All right? And so now we're going to end up with our integral. Let's expand this 2 tan theta. So that's going to be 8 tangent cube theta. Instead of the radical, all this hoopla right here, that's going to be 2 sec theta, since we just simplified it. And then we still have our 2 secant squared of theta from our derivative d theta. All right. Now, at this point, we're going to have to simplify and be able to try to evaluate this trigonometric interval. A couple ways that we can do this. One of which is that if we can get to all tangents and then find a derivative to get the secant squared, then we'd be good. Or if we could split off a secant tangent and get everything in terms of secant, that might be useful to us as well. And I don't believe that we're going to get everything in terms of to get to our tangent just because we have this tan cubed. So it might be best for us to break off a tangent and then get everything in terms of secant cubed. All right. Now we have an 8, a 2, a 2. That's going to be 32. And what I'm going to do is I'm going to break off one tangent. Okay, so when I rewrite this, I'm going to get tan square theta. We still have the sec square theta. We have this secant of theta. And then we also broke off one of the tangents. So we're 3 to start with. Now we have tan theta d theta. All right. And the good news is now we can use our Pythagorean identity on this tangent squared, and then we can get everything in terms of secant, and we know the derivative of secant is secant tangent. All right, so we're well on our way to evaluating this trig interval. Pythagorean identity, sec square theta minus 1. All right, then we have sec square theta, sec theta, tan theta d theta. Now we can use our u substitution. All right, let's let u be equal to secant, not secant square, but secant, because the derivative du is going to be secant theta tangent theta d theta. And that is precisely what we needed. Okay. So now we substitute back in for secant. 32 integrals. U square minus 1. U square. And then sec theta tan theta d theta is going to be our du. All right. And now we finally get down to a polynomial integral to which we can evaluate. We're going to distribute the u to get 32 integrals of u to the fourth minus u square du. And now we're just going to use our good old power rule for antiderivatives. So now we have 32 quantity 1/5 u to the fifth minus 1/3 u to the third plus c. At this point, we're going to go through back substitute. Remember, all the way when we did the u sub, u was equal to secant. Okay, so this is going to be 32 quantity 1/5 secant to the fifth of theta minus 1/3 secant cubed of theta plus c. We still have to back substitute for secant. Okay, now remember, secant is the reciprocal of cosine. Okay, and we know that cos of theta for this triangle is going to be adjacent over hypotenuse. So if we flip both sides over, secant of theta is hypotenuse over adjacent. And that might be a trick when you guys are taking your exams or doing quizzes. So that way you don't have to think in your head, okay, well, you can just write it out and then take the reciprocal of it. Okay, if you're not too keen on your right triangle trigonometry with secants, tangents, and cotangents. All right, so anyway, going back, remember hypotenuse was the x squared plus 4. Okay, so all the way to the beginning. Okay, here's our hypotenuse, and our adjacent is going to be 2. All right, so one possible answer that we can get for this will be 32 1/5 times the square root of x squared plus 4 over 2 to the fifth power minus 1/3 of the exact same thing to the third power, x squared plus 4 over 2, so that's our hypotenuse over adjacent, and then we have our plus c. All right, and that should be to the third power, not to the second power, excuse me. Now, we can simplify this at this point. All right, so to simplify, right, and this is where the algebra can be used to, I don't know, make it look any better, but this is going to be 1/5 times square root of x squared plus 4 to the fifth over 32. So remember, you have to raise both the numerator and the denominator to the fifth minus 1/3 times the square root of x squared plus 4 to the third power over 8 plus c. Distributing 32 and trying to reduce this a little bit, right? We can go ahead and we know that 32 and this 32 is going to cancel, and then 32 over here is going to cancel with 8 and leave us with 4 for that one. All right, so one possible answer after distribution is going to be square root of x squared plus 4 to the fifth divided by 5. minus 4 roots of x squared plus 4 to the third over 3 plus c. All right, nothing wrong with that answer whatsoever. To be able to get to what the computer algebra system might give you, so if you type this into Wolfram Alpha or Symbolab, you're going to have to factor, right? And notice that there's 3 of these square roots of x squared plus 4 that's common between the two terms. And so you can factor that out. So you could factor out square root of x squared plus 4 cube. And that's going to take 3 of those radicals away from each of our terms. All right, so that's going to leave us with 2 here. All right, since we took 3 away. So that's going to be the square root of x squared plus 4 square over 5. And then we took all of them from this. So that'll be minus 4/3 plus c. Now, square and square root are going to go away. That's nice. And after that, that's going to leave us with square root of x squared plus 4 to the third. And then we get x squared over 5, or technically it's going to be x squared plus 4 over 5. But what I'm going to do is I'm going to break that up into 2 separate fractions, because then we can combine the 4/5 and the negative 4/3. All right, so we can rewrite this as x squared over 5 plus 4/5 minus 4/3 plus c. If we get a common denominator of 15 for everything, this could be written as x squared plus 4 cubed. And this is going to be 3x squared plus 12 minus 20 over 5, or 15, excuse me, plus c. This is just going to turn into a negative 8. Okay, so just getting a common denominator, that's going to be a negative 8. Right, and then finally, if we really wanted to, we could factor out that 1/15. And so, admittedly, I plugged this into Wolfram Alpha just to see what the computer algebra system would give me. I did work it on paper beforehand just to make sure I knew what I was doing. Still don't know if I know what I'm doing, but that was the precise answer that I got from Wolfram Alpha, all right, when I simplified it. So not a nice integral, especially at the end when you have to do all of these factorizations. All right, so key takeaways from these basic types of trigonometric substitutions. And when I say basic, I'm throwing my hands up and saying quotation marks basic. Okay, you have to choose the substitution. All right, so that's the first step. Second step is to draw your triangle. Next step is to actually plug in, replace x with the terms of theta. And simplify. All right, and that's probably the longest part of it. Then we have to integrate, right? And that's where we have to use our trig integrals, right? And then the last thing we have to do with these is we have to back substitute. And again, that's where we use our triangle. All right, so these are all elementary examples that we've seen, okay? There are some advanced techniques that we need to look at before we can get out of this section. And one of those techniques is actually going to be a technique you're going to use for those of you that have to take differential equations and higher level maths. It's being able to complete the square to be able to evaluate these sorts of trigonometric integrals. And the next video, we're going to take a look at that.